won't let you resign.
Huh?
They won't let you resign.
Of course they'll let me resign. They don't even care about me enough to like let me resign. There's this joke that like if I were to die, I think the only reason they'd know is because I would stop answering my emails. It's the kind of job I have. I don't know, like being a professor is a lot more than just teaching classes. Like this is supposed to be like the least important part of my job. I spend far too much time with you guys than I feel I should be. Seriously. I prepare slides, I read ahead. Yeah, the slides I give are shit, though. It's true. Well, they didn't give me slides.
That's right. Yeah.
They just gave me, like, some loose collection of notes, which...
What else?
Huh? So, like, the largest part of our job is to write research papers. To, like, look into a topic and to produce research. Like, that's how they measure our worth, basically, by our research output. And then we have to, like, apply for grants, which is in itself, like, a hugely time-consuming activity. And it's bullshit. And since all the refereeing is done, like, anonymously, you get, like, called names, like, quite a bit. Like, you'd be surprised, like, how childish, like, adult professors can act. Because they're all egos.
What research do you do?
So I do something called computer algebra. So you've tried Maple, at least this Maple TA part. So I have nothing to do with Maple TA, but I was a Maple programmer. I was like like I'm the one who told the computer how to calculate an integral in order for it to be able to check your answer. So that's what I was thinking of doing a little bit next week, since I've run out of material, to show you how to program a computer to do math, to see how we can like instruct the computer to automate Gaussian elimination. Because it's not something that humans are supposed to do. It's time-consuming, and so the one I gave you on your exam is a 3x3. So you have to do a 3x3 Gaussian elimination. So don't worry about more than that. And the answer to the first question on the exam is 0. Do you believe me or not? Will 0 even be an option? I want to do true, false, none of the above. So another honors course I wanted to teach is a computer algebra course. That would be cool. Like learning how to do mathematical programming. But how many more lectures do we have left? It's 2 more weeks? 4? No, there's 12 lectures in total. And this is 9 plus midterm, that's 10. So 2 more. Yeah, if you guys want any topics covered, just tell me and I can cover it. Is there anything you'd like to hear more about? That'd be good. Are you guys struggling in the calculus part?
Well, the current part's not too bad, but beforehand it was getting a bit...
It should be getting easier now. Yeah.
Inverse functions are not hard.
What isn't hard?
Inverse functions.
Oh, no, that shouldn't be hard. Just, yeah. Yeah, starting off with those epsilon delta proofs is really like the bad foot forward. But like chronologically, it's the only sensible way to do it.
I've worked on this.
Well, I can tell you assuredly that you can ignore epsilon delta proofs and be fine for your exam. Because there's 2 questions, like there's an epsilon delta proof on your exam, but it's optional. Oh, right, yeah, so you guys never, okay, so there's a bunch of stuff you have to talk about for the exam. Okay, it's good that I remember this. Have you guys filled out a GPAS yet?
Yeah, my name doesn't fit.
Huh? Well, then you automatically fail. Okay, so there's these sheets that you're going to be receiving for your exam, where you have to answer multiple choice questions, but you have to like color in a bubble on the thing. Have you guys used these yet? Here. Okay. Because like they're freaking out in the department about us issuing you instructions about these things. Like in particular, when it asks for your student number, you should not include the C. Apparently that screws up the system. Yeah, the computer can no longer. Yeah, and you have to use pencil. So bring a pencil. Yeah, pencil. Well, I guess pen will work, but it prohibits you from erasing anything. Okay. What? Yeah, I think pen works.
Yeah, on the piece of paper it says you can use pen, but everyone steals it.
What?
On the piece of paper it says you can use pen. If you get a pen out, everyone steals that. Yeah.
That's weird. Put that down! Who gave you that? Tell me who gave you this. Yeah, so your exam is different format than your midterm, because it's a lot more official. So that George told you that the first 20 questions on the exam are multiple choice, yeah? And then it's the best interest for all of you, like as a class, to get the highest marks possible on it, right? Because we're going to use that part of the exam in particular to scale you against the other class. So if you like, what's the Australian word for do well at? Yeah. I want to say crush it. Is that something you guys would say here? Anyways, if you all get 100% on that, then you're like, if the other class gets like a 60, we know you're like that much better. So like whatever their like marks are, you guys will be that much higher. Right? That there's a lot of failures in 1110? I have no idea. But George keeps saying he wants most of you to have like the highest possible grade. Like, how are you graded here? I don't know. Yeah, HG. Yeah, he wants you to. Oh yeah, he all wants you to have HG's high distinction. Yeah. Okay, so we want most of you to be able to get high distinctions. Well, yeah, we're going to try to get you some past questions. So me and George were looking at the like it's done, and we both kind of feel that it's easy, like the multiple choice, like almost too easy. No, we just took the 1110's multiple choice. Huh? So you're going to be taking like, yeah, their exam basically. So you take their exam plus another exam. They're only going to do the 20 multiple choice questions and then maybe like a handful of short answer ones, which are like so easy. So you have to do the 20 questions and then 6 short answer and then 2 long answer. So they'll be late for that, my friend. We lost almost half. Like we started with 80, now we're at 50. No, in 1210. Why would you go to class to unenroll it in? Free internet. That's weird because we basically flipped a coin as to who would be doing what side. Like originally I was supposed to do the calculus side. Then we switched back. So I don't know. I'm actually way better at calculus than I am at this. Huh? Well, I don't know. I don't think anyone's really good at this. It's hard teaching things that are basic. Like I think this is the hardest I've ever had to work to like figure out how to. It's just hard trying to explain something that seems like very obvious. Well, don't mean to denigrate you guys, right? But like, how could you talk for 2 hours about complex numbers, right? It's like you add the first part, you add the second part, repeat sheet. Yeah. Okay, so it might be probably will be a short one today. This is the last of the material that we have to cover. You guys, have you finished your assignments yet? They're due next Tuesday, yeah?
Alright, thanks.
You guys been managed to download it and look it through?
I haven't looked at it.
Haven't looked at it. Fantastic.
There's some bits. Yeah. Half the song is whatever videos, and some don't have like actual like visuals connected to the audio.
Oh.
Yeah, but then I can watch it on my iPad.
Yeah, I don't know. It's really a little bit out of my wheelhouse.
I'm looking at the point here, the assessment work, like the ones that are handed.
Got 3% each or something like that. Yeah. And the maple's worth another 10. Yeah, we'll give you more maple to prepare for the exam. Yeah. I guess I should do that soon, eh? I'll try to get some algebra questions up this weekend. Yeah. Oh, and we extended the deadline for the Maple TA stuff to like the end of term. So if you didn't finish your complex number stuff, you can still log in and do it. You all should get 10% for the Maple TA stuff. Yeah, we won't count those towards the total. Yeah. Yeah, we can't fix questions or it boots you all. So I can fix them, but then you'd all have to start over again. Huh? Yeah, I'm just not going to count them towards the total. Okay, so today we're going to talk about operations on matrices and how to invert those matrices. So recall that last week we were talking about matrices. And in particular, we defined a few operations over those matrices. So the first one that we defined was the matrix sum, which is the easiest. So if you have two matrices, A and B, and they have the same dimension, that is, they have the same number of rows and the same number of columns, then you can add those two matrices together simply by adding their entries, component-wise. Right? So the entry in A plus B at 1, 1 is the 1, 1 entry from A plus the 1, 1 entry from B, and so on. You can do the difference in the same way, except these additions here are going to become subtractions. We also define the scalar matrix product, that is taking a scalar and multiplying a matrix. This doesn't really need a definition because this is just A added to itself C times, and we just define the addition. But anyways, this just takes every entry of A and scales it by the scalar C. We defined something a little bit, before we cross product, we defined how to deconstruct a matrix A into its rows and columns. So recall rows are these, and columns are these. So the ith row of A was what?
You've got the ends and ends mixed around.
Yes. Where's my corrector? This should be m by n. Right, this is n columns and m rows. Thank you. So I can say we can pull out the ith row of A by using this. Right, so the first position should be I because that denotes the row. And to pull out a column, we can use this, and we simply just take the column with a j in the second position. So this is the jth column. So I guess the most complicated operation on matrices we defined was that of the matrix product. And the ith jth position in the matrix product is the dot product of the ith row of A and the jth column of B. And that was illustrated by this picture. Right? So if we want the element that's in the second row, third column, we have to take the dot product of the second row of the first matrix and third column of the second. Right? So this is 8 plus 18 plus 0, which is 26. Right? Here's another one. If we want the matrix, if we want the position that's in the first row, fourth column, let's going to be the dot product of the first row of the first matrix with the last column of the second, which is 3, plus 2, which is 5, plus 8, which is 13. Okay, so what kind of properties do these operations have? And then what type of algebra do we have with matrices and these operations? Well, first, notice that matrix multiplication is not commutative, for sure. Right? So let's just check 1. Right? So consider the matrix -1, 0, 2, 3, and 1, 2, 3, 0. Then what's the product of A, B? We're going to do a lot of these today. Okay, so what should the dimension of A times B be? 2, 2, right? Because this is 2, 2, and this is 2, 2. So let's just do the first position, right? So the first position should be the dot product of this row and this column. So it's -1 plus 0. -1. Okay, so let's do the second one now. That should be the first row and the second column. That's -2 plus 0. -2. So let's check. Hooray! -1, -2, and I take it you guys can do the last one. Okay, so let's find the first position of B times A, right, this way. So that's going to be the first row, 1, 2, times the first column, -1, 2, so 3. Perfect. 3, 6, -3, 0. They're not equal to each other. Very good. So that means that matrix multiplication cannot be commutative, right? We found one counterexample, and that is sufficient. So if I ask you on your exam, is matrix multiplication commutative? You will answer none of the above. Okay, so since matrix multiplication isn't commutative, we have to make a distinction between multiplying something on the left and multiplying something on the right, right? Because these values are different, or can be different, right? So we call this the left multiplication of A on B, for obvious reasons. And here, we call this the right multiplication of A on B, for obvious reasons. And these are not necessarily equal, but can be.
Why don't I just say the left multiplication of B on A?
You can do that. This could also be considered the left multiplication of B on A and the right multiplication of B on A. You just have to pick one that's fixed, right? Or you're usually taking something and choosing to multiply it by something else. And that will dictate which is left and right. Okay, so beckoning back to our first lecture, since we have a group of matrices with addition and multiplication, we may or may not get a ring or a field. These are some of the properties that fall out of these operations. So in particular, matrix addition is commutative. Right? So first we have to assume that everything defined here is defined in such a way that these will work. Right? So A, B, and C have the correct dimension so that A plus B is possible. Right? So we have commutativity of addition. We have associativity of addition. Right? That's the one where we can move the brackets. But we have associativity of matrix multiplication. We have distribution from the left. Right? B plus C times A is BA plus CA. We have distributivity from the right. That is AB and AC is equal to AB plus C. And then a whole smattering of other ones that just involve scalars. Right? So this is the distributivity of scalar sums. This is the associativity of scalar multiples. And this is the associativity of one scalar and a matrix product. Right? So these are all rules that we can use to simplify matrix expressions. Okay, so I'm going to prove the left distributive law, this one. Okay? So let A be an n by n matrix, and let B and C be n by L matrices. Then we want to prove A times B plus C is equal to AB plus AC. So first let's check that these have the right. Was this the right? Yes, that should be right. Jeez, you're getting so good at taking my mistakes, now you're finding them ahead of time. Next time I'll just send you these slides for proofreading them the night before. How does that sound?
Okay, that's all fine.
Yeah. So let's first check that this is actually a well-defined expression. So B plus C is going to be n by L. A is R by n, so this should be what? What's the dimension of this? N by L. M? No. N. Oh, it's wrong again. This should be switched again. This should be M by N. Okay, so if this is M and this is N, then what should this be? M by L. And this will be M by L, and this will be M by L, so their sum will be M by L. Okay, so at least that it is the case that the dimensions work. Okay, so recall that if I just say A sub ij, this denotes the ith jth entry of the matrix A. And also recall that two matrices are equivalent when all of their entries are the same. Right? So if I can show that the ith jth entry of this is the ith jth entry of this, then we've shown that these two things are equal. Yeah? Okay. So let us give, what is the ith jth entry of this? What is the definition of matrix product? Right. So it's the ith column of A, ith row of A, dot product the jth column of B plus C. Right? Okay? How can I expand this now? Right. This can be expanded to be the jth column of B plus the jth column of C. Right? And we know that the dot product distributes over this sum. Right? So I can do this. Oh, and yes, so these both are the definition of the cross product. So we know that this is the ith jth position in A cross B, and this is the ith jth position in A cross C. So in the end, we have that this is the ith jth position of AB plus AC. Right? So we've proved that A cross B plus C is the same thing as A cross B plus A cross C. Right? So these are how these linear algebra proofs sort of pan out. No one likes doing them. Or like maybe people who hate themselves like doing it. Because they usually involve a lot of arithmetic on these indices, and it gets kind of messy. Okay, so to illustrate that matrix multiplication is associative, let's check that AB times C is the same as A times BC. Right, so what's AB? Maybe if you can give me the first position and like the last position. Well, first, what's the dimension of AB? 2, 2? Yeah, because sure. 3, 2. Because this is 3 rows by 2 columns and 2 columns by 2 rows by 2 columns. So the product should be 3 rows by 2 columns. Okay. So what's in the first position here? It's 4 plus 4. So it's 8. Right? 8. Okay, what's in the one below it? That should be the dot product of this row and this column. So it's 12. 12 plus 8 is 20. And underneath that should be 0 plus 2. Great. Okay, so now we want to take AB and multiply by C. So this is 3 by 2, this is 2 by 2, so the product should be 3 by 2. This time I'll just give it to you. So we get that. Okay, so just sort of try and remember this. So on the next slide, oh no, that's A. So here's BC. I pre-computed it. What's that multiplied by A on the left?
3 by 2.
3 by 2. What's in the first position? It's this row times this column. 10 plus 8, 18. Right? And that should be the same as the matrix from the page before. Right? It's not. 1846, 4. 1539, 3. Who said it wasn't? You shut your face. Okay, so we've at least confirmed that matrix multiplication is associative for this example, as we expected. Here's a question. Do we have additive and multiplicative 0 for matrix arithmetic? Do you remember what the additive and multiplicative 0 is of a group? Yeah? Okay, so is there an additive 0? Yes. The matrix of all zeros, right? And you can imagine what happens when you take the matrix product of a matrix with the 0 matrix. You'll get 0 back, right? So there is both a 0 for addition and multiplication. And as you said, it's the matrix comprised entirely of zeros. Right, so let this bold 0 n by m denote an n by m matrix comprised only of zeros. Right, so here's, did I screw this? Oh no, this is right now. N rows, I'm even surprised. N rows, m columns, all zeros. And clearly, if you have a matrix A of the correct dimension, n by m, then A plus 0 is 0 plus A is A. A minus A is 0. 0 minus A is minus A. And A times 0 is 0, and 0 times A is 0. This should be a bold 0, is my corrector. Okay? So yes, we do have multiplicative and additive 0. Falls out straight from the definitions. Okay. Next question, harder question. Do we have additive and multiplicative inverses for matrix arithmetic? Okay, so what's the, if we're working over the integers and I say, what's the additive inverse of 7? Minus 7. So there's clearly an additive inverse. There's clearly an additive inverse for matrices. Right? I give you a matrix A. Its additive inverse is as a matrix with all negative versions of its entries. Right? Okay. What about multiplication? Right? What would a matrix inverse look like? No. But like, what is the multiplicative identity? Right, so when we inverted fractions, right, the multiplicative inverse of 2 was a half, because 2 times a half is 1, right? And 1 was our multiplicative identity. So what is the multiplicative identity? Can't be 0, right? It needs to be an entry that you can multiply, which doesn't change the thing that you're multiplying. 7 times 1 is still 7. So I guess the question I'm asking is there a matrix, if I give you A, can you give me another matrix which I can multiply by A so that the original one doesn't change? 1's on the diagonal. Right? So for multiplication, it depends. But we have an answer for this question. Right? First we must consider what our multiplicative identity is. So the question is really, is there a matrix, say I, with the property that A times I on the right is A, or A times I on the left is equal to A as well? Right? This is like a 1. And as you said, the matrix that satisfies this is called the identity matrix. We sometimes subscript it by n to denote that it's the n by n matrix. Oh, and it is always square. It's an always square matrix with 1's in the diagonal and 0's everywhere else. Right? We typically just write I instead of in because when we're working with I, it's usually implied what we want the dimension to be. Like we would never define the identity matrix with the dimension which wouldn't work. Right? So when you see it in an expression, just assume it has the correct matrix dimension. Okay, here's a proposition. Let A be a n by m matrix. Then, if I multiply on the right by the m by m identity matrix, I get A. And if I multiply on the left by the n by n identity matrix, you get A. I think my dimensions are right. Yeah. Okay, what is the ith, jth entry of A cross product the identity matrix. Yeah, the ith row of A dot product the jth column of the identity matrix. Right? In particular, if we expand this, because this is full of zeros except for the jth position. Right? If this is the jth column of I, the only non-zero entry is in the jth row. Right? The only non-zero entries are in 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. Right? So here this will be JJ. Right? So if we take this dot product, there will only be one non-zero term, and that non-zero term is going to be Aij. Right? So the ith jth entry of A times the identity matrix is Aij. Right? So these are equal. Right? So I'll leave it to you guys to prove it from the other side. It's the exact same proof. Right? Is that clear? Yes. Okay, so what happens if we take an identity matrix and multiply it by something that isn't square? Do we still get the same matrix back? Well, we just proved it, so we better. But let's check. What's in the first position here? Well, this is 2 by 2, and this is 3 by 2, so the result will be 3 by 2. It's 2 by 2. No. 2 by 2. This is 2 by 2 and 2 by 3. So this is 2 by 3. You are correct. I'm sorry. Oh, boom! So what's the position here, right? It's this row times this column, x, right? Y, z, okay. Right, so it does give you back what you want. Right, if we do the same thing from the right, which means we need a 3 by 3 identity matrix, right? Because this is 2 by 3, this is 3 by 3, the result would be 2 by 3, 2 by 3. So the first, it's going to be first row times dot product first column. That's 1 and zeros, and the rest pans out like this. Okay, so here's the definition of invertibility. If I give you a square matrix A, this matrix is invertible when there is another matrix that's square, call this A inverse, such that A times A inverse is equal to A inverse times A is equal to I, the identity matrix. Right, so our inverses are going to work both on the left and the right, and in order for this to be able to multiply A from both sides, everything has to be square. That's the only way for the dimensions to work out. Right, so when we're talking about matrix inverses, it is assumed that we're always starting from a square matrix. Right, so that's what I'm trying to get across here. Because this inverse has to work on both sides, it forces the dimensions to be the same. Here's an example. The matrix 3, 5, 1, 2, B, is the inverse of the matrix 2, minus 5, minus 1, 3. Right? Because if I multiply these two things together, I should get the 2 by 2 identity matrix. So let's just check that this is a 1, and the thing underneath it's a 0. So the first one is 6 minus 5. That's a 1. And the thing underneath it is going to be a 2 minus 2. That's a 0. Right, so boom, we get I. Right, so B is the inverse of A. Also, though, A is the inverse of B. Right? It works both ways. Doing it from the left now, let's check again that there's a 1 and a 0. So the first position is this, dot product this, which is 6 minus 5. That's a 1. Underneath it's going to be minus 1 plus 3, which is 0. So again, we're good. Right. So indeed, we have this multiplicative identity in this identity matrix. Is every square matrix invertible?
Yes.
Who thinks yes? Who thinks no? Wow, not all of you voted. Okay, the answer is no. So who thinks yes? I like your convictions. Who says no? How can you still not vote? Who's on the fence somehow? I don't know, he's trying to trick us. Obviously not. Right? 0 times anything is 0. Right? So 0, you cannot find a matrix inverse for 0.
Wouldn't it just be 0 then?
No, because it's a number that you have to multiply to get 1 back. Right?
Infinity.
That's not a number. It's like, that's a concept. Right? That's a whisper of a number. Was there a question?
You want to have 0.
This is a matrix. You can't do what? A plus for you, man. A plus. This matrix is not invertible. I can prove to you why. Right? Okay, so we want to multiply this by something in order to get the identity matrix back. So take any B, anything, right, and ask what the third column of B times A is. Right? We know that this column should look like what? 0, 0, 1. Right? So let's see what we get. So the third column of B cross A is the first row of B, dot product the third column of A, and so on. Right? But the third column of A is 0 in all cases. Right? 0, 0, 0. So here we get 0, 0, 0. Right? No matter what our selection of B is. This isn't equal to 0, 0, 1, right? Which isn't the third column of I. Right? So this can never be equal to I. Right? For any selection of B. Right? Thereby, A cannot be invertible. Right? In the subsequent class of this, you'll learn why. Right? And you'll learn how to test for this a priori.
So if you have a matrix that has no series and it's square, does that mean it's always on the inverse?
Not necessarily, because you can do like row operations to make zeros.
So we can't simplify that to 0. We could.
Basically, yeah. Right, so that's actually my next point.
Oh, right.
Oh, no, it's not. In your next class, you'll learn how to tell if a matrix is invertible or not. Right? These are called singular matrices, the ones that are not invertible. And you need the determinant in order to do it. I'm not allowed to teach you the determinant. That's a concept too. It'll like blow your little minds, apparently, if I show you how to take a determinant.
We already done it.
Huh? I showed you how to do a 2 by 2 one. That's barely learning how to do a determinant. Could you, if I gave you a 5 by 5, do you know how to do it?
Eliminate columns.
Okay, yeah. This cofactor expansion is not trivial. Anyway, you'll learn that next semester. You won't have me. You'll have a good prof who will teach you something. Okay.
But he won't bring pornography.
He won't bring pornography or talk about drugs. Or who knows? Who knows? Maybe you'll get lucky. If B and C are inverses of A, then B is equal to C. That is to say, matrix inverses are unique. Right? They're not. You can't. There is no two matrices which will take A to the identity matrix. Right? So I can say it like this: if AB is equal to BA is I, that is, if B is a matrix inverse of A, and AC is equal to CA is equal to I, that is, C is a matrix inverse of A, this means that B is C. Right? Matrix inversion is unique. Okay, let's prove this. Right? So towards a contradiction, right? Remember, which is this tagline to indicate that I'm going to write something that's incorrect. Suppose there is B not equal to C, such that both B and C are inverses of A. Okay? Thereby, we have B times A is the identity, which means B times A times C is the identity times C, which is C. Right? So we've shown BA times C is C. We also have A times C is the identity, right, from our assumptions, which means BA times C. Oh, sorry. We have BA equals C. We have by associativity that BA times C is the same thing as B times AC, right? Moving the brackets is just associativity. We know that AC is equal to I, so this is equal to BI, which is equal to B. right, by associativity. But look, we have BAC, BA times C is C, and BA times C is B. Thus, B is equal to C. Yes? This contradicts our assumption that B is not equal to C. This is a contradiction. We are done. You like this contradiction? You're going to use this on your exam, even if it has nothing to do with the question. Find the nearest distance to the plane. I won't, but what I will do is prove that matrix inversion is unique. Yeah, but so this is the type of stuff you'll do in a general algebra course. So I'd recommend that you take it. These types of proofs are quite fun when you start getting into them. I am. Okay, so since inverses are unique, we can just talk about the inverse, right? Instead of talking about... You have a question? Someone? Oh, they're just playing a game. I wonder if it's good. Okay, so if A is an n by n square matrix, the inverse of A is denoted A inverse, and it satisfies, well, right multiplication and left multiplication gives you the identity in both cases. Proposition: if A and B are both square matrices of dimension n, then A times B is invertible, and in particular, AB inverse is equal to B inverse A inverse. Right? So it's invertible, and in particular, the inverse is given by this. Let us prove this. Right? Notice that this is I. Right? So A inverse times A is I. B inverse times B is I again, the identity. Right? So this is the identity. Yes? Okay. We also have that this is the identity. Right? Because B times B inverse is 1, or the identity, and A times A inverse is the identity. Right? So this is the identity as well. So what is the inverse of AB? Right? What have we shown? That if I multiply AB on the left by B inverse A inverse, you get the identity. And if you multiply AB on the right by B inverse A inverse, you get the identity. So that means B inverse A inverse is the inverse of AB. I still look some confused. So we're looking for, in order to, so...
Are you just proving it by saying that it's correct?
What do you mean?
Well, you're saying that the inverse is equal. Like, I don't understand how you're expanding that.
This part.
Yeah.
So you see how in the middle here this will become the identity,
Yeah.
and this will become the identity,
Okay, sure.
right? So I found something to multiply AB by to get the inverse, right? So
You can see why you teaching basic stuff is hard.
when you have to prove something that looks really trivial, it's hard to know what you should be proving and what is assumed. But anyways, I found an element that I can multiply on the left on AB and on the right by AB to get the identity. Thereby, this is the inverse. Right? Like in particular, right? So I found the inverse. So both of these must be true. Okay, so more generally, the product of any number of invertible matrices is invertible. And the inverse of the product is the product of the inverses in the reverse direction. So this is a little bit easier to understand as a formula. So if I have n plus 1 matrices A naught through AN, and they're all n by n, then the inverse of this product is the product of the inverses, but you have to reverse them. Right? So this is AN inverse through A naught inverse. So you guys can try to prove that one on your date night or whatever. Okay, so we've been talking so much about inverses, so how do we find the inverse of a matrix? Well, for 2 by 2 matrices, which are the baby matrices that you know how to take determinants of, there is a method for calculating the inverse. So simply, the inverse of a 2 by 2 matrix given by A, B, C, D is 1 over the determinant of that matrix times, and you swap the diagonals, right? So AD becomes DA. Huh? AD minus CB. The product of this diagonal minus the product of that diagonal. The inverse. You'll learn about tons of its uses next term. So I think we used it more in the cross product. Because the cross product ended up being a determinant of a particular matrix that we've taken. Anyway, so the matrix inverse of A is given by this formula, right? You divide by the determinant, you swap this diagonal and you swap this diagonal, but you make it negative. Okay, so here's a proof. So this is the formula for A inverse that I just gave you, and here's A. And to prove it, we simply just need to simplify this and see that we get the identity matrix back. Right, so if you take the cross product, you end up getting this. So notice this is BD minus BD, which is 0. This is AC minus AC plus CA, which is 0. And both of these are the determinant. Right? So if I divide through by this, you should get 1s in the diagonal, which you get the identity. So for an exercise, do the other one. Okay, what's the inverse of A?
3 minus 1 minus 2, 1.
Well, first, what's the determinant? Determinant should be a scalar, one number. Determinant is 1, right? 3 minus 2. Right? Okay, so we have to divide by 1, so let's forget about it. Then we need to swap these elements and these elements and negate. So I think you're right. 3, negative 1, negative 2, 1. Okay. What is the determinant of B? 6 minus 4 is 2. And then we have to swap this diagonal, and negate. I would recommend that when you're taking these inverses to leave this as a fraction. Just leave it out. Because when you multiply multiple matrices, then you can just multiply the fractions in front of them instead of putzing around with them inside. What is AB inverse? What's the determinant? Is that right? Okay. Yes. So this one I actually multiplied in. Right, so it's quite trivial to determine the inverse of a 2 by 2 determinant. All right, so to confirm our proposition, that is the inverse of AB should be equal to B inverse times A inverse in that order. Let's do B inverse times A inverse. Right, so here's B inverse, here's A inverse. The first position is what? 3 plus 1 is 4. Underneath it, we're going to get minus 3 plus 3 halves. No, I don't want to do fractions. There you go. In the end, we get 4 minus 3 minus 9 halves, 7 halves. And that is the same as this. All right, so at least for this example, we've confirmed that the inverse of AB is equal to B inverse times A inverse. Okay, we can also take matrix to higher powers. So if we let A be an n by n matrix and m be a non-negative integer, a to the power of m, or the mth power of A, is given by this formula, which may kind of look weird, but a to the power of m is equal to the cross product of A times a to the power of m minus 1, so one lower power, where a to the power of 0 is given to be the identity. Right? So you just keep expanding this until eventually you hit 0, and then you could stop. Right? We can also do it when the exponent is negative. Right? So, moreover, a to the power of minus m is equal to a inverse, and this should be a m, not a minus 1. Here's a couple of propositions which you can practice on. If A is a square matrix and Rs is an integer, then as usual, the exponents add when you multiply, and the exponents multiply when you take subsequent exponent powers. So that's an exercise. Here's a proposition. If A is invertible and K is a non-zero scalar, then A inverse is invertible, and the inverse of A is A. Right? So it brings you back. Right? So the inverse of the inverse is the original thing. If A to the power of n is invertible, and this is a statement. An is invertible, and A to the power of n inverse is equal to A inverse to the power of n for all finite values of n. Right, so this just means you can switch these powers and inversions. And A times a scalar is invertible, and in particular, Ka inverse is equal to 1 over Ka inverse. Okay, so let's prove 1. Okay, so A inverse is invertible, and A inverse inverse is A. Okay, well, clearly, A times A inverse is equal to A inverse times A is equal to the identity, right? So what is the inverse of A inverse? I know this seems kind of strange, right? But I found a matrix, A, so that left multiplying A inverse and right multiplying A inverse gives you the identity. Right? So by definition, A inverse inverse is A. Right? It is the thing that you multiply A inverse by to get the identity back. So this is another example of a simple proof that looks kind of circular. Right? But this is certainly true, and by definition this is true, so it's proven. Yeah. Okay, here's another one. If Ka is invertible and Ka inverse is 1 over Ka inverse. Well, using the rules of matrix arithmetic, we can write Ka times 1 over Ka inverse. This is equal to right, 1 over Ka inverse. I just take this scalar out, which means I can write 1 over Kk times A inverse, which is equal to 1 times I, which is equal to I. Right, so again, I just showed that this times this is I, and thereby these are each other's inverses. You can also do the same thing, multiplying Ka on the right, and you'll get the same result. I think I'll need a break soon. You want a break now? Okay, go take a break. 10 minutes. Huh?
How many more slides do you have?
There's a lot more to go. Holy crap, there's a lot more to go. I thought it was going to be a short one.
I have a
It's chilly today. Is it? Is it abnormal?
No, not when we have this one. When it flies off the desert, it's pretty cold. So we're having a south, oh sorry, west, southwest. I was in Walker on the weekend and there was frost, ice over everything. I had to chip it off my bike before I
You should go check out the desert. I've heard many things. There's that huge rock that I can go see.
yeah.
What's it called?
Uluru, Ezra. It's a long way to go, Jeff. It's a long way. But if you do drive, go down to Adelaide or near Adelaide and you drive up, it's much better. As the latitude changes, the desert changes a lot, plus you'll go through the Flinders and the Flinders.
Yeah, I should check out this country a bit. Can't spend 2 years in New England.
That's alright, New England's alright.
I like New England.
But it's just, it'd be like driving across Canada. It's just really, really big. But Canada changes.
Well, it depends. There's like this big thing in the middle, which is like infamously boring. No, it's plains. It's where we grow our wheat. You basically just, for 2 days, you're just driving straight. And it's like the same, like farmhouse that goes by. Like, it's like in the Flintstones, you know, this like would recycle the back. That's how it feels like driving through Saskatchewan. They say you can fall asleep and wake up and still be like.
Australia's like that when you drive across, as you drive up, it changes every few hundred k's. Not markedly, but there is change.
Well, depending which way you come from, like, you'll get to the Canadian Rockies, right? And then things change from straight to, I'm gonna die, I don't want to die. Like driving up and around these like steep cliffs. And
Yeah, like New Zealand.
it's another place I have to head out to.
I've moved there.
There's positions in Christchurch, obviously, at the uni. Did we move to New Zealand in a second?
Oh yeah.
But it's like a more isolated Australia.
Yeah.
What's the downside?
I miss the real world.
New Zealand's actually, because they're even more isolated than us, they're actually, in my opinion anyway, more connected with what's going on in the rest of
You reckon?
So they can ignore it because it's like it's not so far away, so you can ignore it. When it's actually a lot farther away, you don't ignore it. You know, so their internet's good. You know,
Their internet's good. Maybe I will move to New Zealand.
Last time I was, I moved to Australia 3 years ago.
Yeah.
But they seem to know what's going on in the rest of the world. Australia doesn't.
You guys don't need to.
Well, that's right. You don't need to if you think you can at any time. But when you don't think you can at any time, you actually make the effort. But picturesque. Just
Yeah, I'll make my way over there. I could have gone when I just moved here. My friend went to New Zealand. She's like, "You should come." I'm like, I can't. I just started working. I can't take a vacation. It's like my second week here. It's like, oh, I'm exhausted. I'm gonna gotta go take a vacation. I need a 2-week vacation for the 1 week I've been here. Is it?
The living is more expensive over there, but fuel's very cheap. So if you get a camper van, something like that,
And car's cheaper as well.
it's a really good holiday. It's
Do
if you go between seasons. It's not, summer's a peak season and winter's a peak season. If you go between, it's less than half price.
I can go check out the Lord of the Rings stuff.
Yeah, that's about it. We can go look at the sheep farms.
Don't laugh, but
That's what they got, right? Eye of Sauron and sheep farms. Or I can drive around Australia to look for all these like giant things that you built, like the world's largest lemon. Or oh yeah, the big prawn. Well, my friend like came here and did this trip. She just went and checked out all of these like giant versions of things.
Yeah, it was a little typo. And then when the price is everything burned except the prawn.
Except the prawn.
Just a lone prawn.
I have a funny story about these type of things burning down. So in the States, there's this one church, and they built an enormous bust of Jesus, like enormous, like doing this, like into the sky, like bigger than this building. And the first time I drove by it, the following day it was struck by lightning and just burnt down. Because the thing was built like totally out of styrofoam, so like completely. Let's see, a giant Jesus bust. It has a name, but Touchdown Jesus. That's what it's called, because he's doing the touchdown. Like that. That's it. That was the thing that was struck by lightning. What? Questionable website. Yeah. Touchdown! Yeah, but that was struck by lightning. But imagine, like, I just drove by this on the highway. I'm like, is that an enormous bust of Jesus? It is. Not there anymore because it was on fire. Let's see if I can find it. Oh, that is not.
You think you'll come back 3 days later?
Oh. Oh, we're all going to hell. Okay, let A be the n by m matrix. The matrix transpose of A, denoted AT, or transpose, is the m by n matrix obtained by swapping the rows and columns of A. That is, the ith column of A transpose is equal to the ith row of A. Right? And in particular, the entries are given by this. The ith jth entry of A transpose is the jith entry of A. Right? So we've just swapped the rows and columns. Okay, so if A is given by this, it's the n by m matrix. Its transpose is given by this. And notice that we now go from A naught naught to A naught m. And now we go from A naught naught through A naught n. And Similarly here, instead of having an n naught, we have an m naught. What is the transpose of B by rows? So what's the first row of B? B transpose. So we want to make the first row of B transpose is the first column of B. So it's 2, 1, 5. And that's the first column. And then 3, 4, 6. Right? The first row of B transpose is the first column of B. The second row of B transpose is the second column of B. Okay? What is C transpose? That was an easy one. What's D transpose? 4. The trace of a square matrix with this as its diagonal, A naught naught through A n n, is given by the sum of the elements in the diagonal. That one's easy. So the trace of B, when B is given like this, is -1 plus 5 plus 7 plus 0, which is 11. Right? Not too complicated. Okay, so assuming the dimensions of the matrices A and B are such that the corresponding operations are well defined, you'll use it next term. Or like it's used to yeah, I don't know why I included it. I thought it was going to be useful, but it's good to know that it exists. You can tell, I'm not even going to try. It will tell you things about the matrix. I can't tell you in particular, but you can know things if the trace is 0, for example, or you can get things about the trace of like the product of matrices.
So it's magic.
Yep, magic. You okay? Can I move? Okay. We have that the transpose of the transpose is the matrix originally. Right? That should be obvious. Swap the rows and columns and swap the rows and columns again, and we get back to the same matrix. We have that the sum of A and B transpose is the individual transposes summed. So A plus B transpose is A transpose plus B transpose. And the same is true for the difference. A minus B transpose is A transpose minus B transpose. And we have that a scalar times A transpose is K times A transpose. Finally, AB transpose is equal to B transpose A transpose. This is very similar to the one we had about inverses. So let's do some proofs. Let's prove that AB transpose is B transpose A transpose. So what is the ith jth entry of this? Let's do it in 2 steps. Right. So the ith jth entry of AB transpose is simply the j'ith entry of AB. The j'ith entry of AB is given by the j'th row of A dot product the ith column of B. We can continue by changing row to column. Right? So the j'th row of A is the j'th column of A transpose. The ith column of B is the ith row of B transpose. And from here, we can swap these because the dot product is commutative. And finally, this is the definition of B transpose cross A transpose. And it is shown that AB transpose is equal to B transpose A transpose. Okay, more generally, we have that the transpose of a product of any number of matrices is equal to the product of their transposes in reverse order, exactly similar to that of the inverse. So if we let A naught through AN be matrices such that A naught times A1 times through AN is a well-defined product, then A naught through AN transpose is equal to AN transpose through A naught transpose. And you can prove that as an exercise. You'll need induction. If A is invertible, then A transpose is invertible, and in particular, its inverse is given by this. Right? So the inverse of A transpose is equal to the transpose of A inverse. Right? So this is handy, because it's really easy to take the transpose of something by like changing its columns and rows. So here's a proof. Notice that A transpose times A inverse transpose is equal to, by what we just showed on the slide before, A inverse A transpose. Right? Because if I put the transpose back in, we have to reverse the order. A inverse A transpose is I transpose, which is I. Right? So I've shown, and similarly, if I multiply on the other side, we have the exact same deduction, and the result follows from this. Right? I found that if I multiply A inverse transpose by A transpose, I get I. And if I multiply A inverse transpose on the right by A transpose, you get I. So these are the inverses of one another. Right? So, okay, so consider the inverses of A and A transpose. So what's the inverse of A? Well, what's the determinant of A? -5 plus -6.
So it's 1.
Yes, it's 1. Right? And then we swap the diagonal. There is a missing negative. That should be negative. And swap this diagonal and negate it. So -3 becomes +3. This should be a minus. That's wrong. Yeah. And it's the determinant here is -5 minus -6. So again, 1. We swap the diagonal here and swap the diagonal here and invert it. Did I just do this? Oh, no, that's different. Which one? Did I not swap them? Is this the first time that I made this mistake, or is it consistent? Well, purple math. Yeah, me too. That's racist. Holy internet. Okay, so here I did a bunch of determinants. Did I not swap them? You're right. Sorry. You don't swap them. You only swap this row and you negate this row. I apologize. So I've been consistently correct in what I've written, but perhaps I've been saying things wrong. Okay. I apologize. See, even I screw this stuff up. Where were we? Okay, so let's try this again, but properly. The determinant of this is 1. We swap the main diagonal. This should be a minus, and we negate the off diagonal. We swap the main diagonal and negate the cross diagonal. Right. And notice that the inverse of A transpose and the transpose of A inverse are equal, which is what we would expect them to be from the result from the page before. Another break? Okay, so I told you how to invert 2 by 2 matrices, but what about larger ones? First, I need to tell you what an elementary matrix is. So an n by n matrix is called an elementary matrix if it can be obtained from the identity by performing elementary row operations. Right? That is, this n by n matrix corresponds exactly to a linear system with single solutions. Right? If you want to look at it in terms of, if you take a matrix of a linear system which has all zeros and you augment it, you should be able to do row operations to solve it. Every elementary matrix is invertible. So thereby, if you can go from In to A, then that means A must be invertible as well. If A is an n by n square matrix, then the following statements are equivalent. A is invertible if and only if AX equals 0 has only the trivial solution. Right? This is a linear system, which is if and only if the reduced row echelon form of A is IN. And finally, A is expressible as a product of elementary matrices. This one isn't too important. This is just the proposition you require in order to prove what I'm going to show you next. But this is the main meat of the procedure. Right? So if nothing I said up till now made sense, this is all you need to know. Right? Let A and B be two square matrices from Rn by n. If you take A and you put its elements into a matrix like this, right, where you put the elements of A here and you put the identity matrix here, if this matrix is similar to a matrix where there's the identity matrix in the first block and B in the second block, then B and A are inverses of one another. Right? So remember, this symbol similar means that I can take this and perform row operations, elementary row operations to obtain this matrix. Right? So you see what we've done? We've taken A, we've packed it into the first block here, thrown in the identity matrix, and then we'll do some row operations to obtain this and find the inverse. So here's a example. What is the inverse of this 3 by 3 matrix? Well, first we construct the larger matrix where I put the elements of A in the first block, right? So 1, 2, 3, 2, 5, 3, 1, 0, 8. Here's the identity matrix. And then let's use row operations to produce the 3 by 3 identity matrix here. Right? So this is something familiar from last week. I need to get rid of this and this. So to get rid of this, I want to add -2 times this row. To get rid of this one, I want to remove 1 times this row. So what do we get? 1 minus 1 is 0, -2, 5, -1, 0, 1. And we get 0, 1, or 3 minus 6 is -3, plus 2, whatever. It's this. Right? 1, 2, 3, 0, 1, -3, 0, -2, 5. And then it propagates in the identity matrix as well. Okay? Now we want to get rid of this one by subtracting twice this row. So we should expect to get a 0 in this pivot. And we do. Right? And now we have to remove what's above this pivot. Well, I guess first we can make it positive. And then I can remove this and this by subtracting 3 times this row and 3 times this row. Right? So you have 0 pivots now here. Finally, we have to get rid of this 2 by taking this row and subtracting twice the first. Right? And finally, we get this. Right? Right? So this should be the inverse of the matrix that we started with. Right? So let's check. Right? So this was our original A, 1, 2, 3, 2, 5, 3, 1, 0, 8. We are claiming that the inverse is this matrix, so let us verify. These are kind of big, so I did this. So -40 plus 32 plus 9 is 1. 26 minus 25 is 1. 15 minus 6 minus 8 is 1. 13 minus 10 minus 3 is 0. 5 minus 4 minus 1 is 0, and so on and so forth. So indeed, we do get the identity matrix back. Right? So this is a general method for determining the inverse of a matrix A. Right? You take A, you augment it with the identity matrix, and you perform elementary row operations to try to get an identity in the right-hand side of the matrix. Okay? Note, though, it is not always possible to invert a matrix. What is the inverse of this, for example? Well, undefined. Yeah, you're right. Right? But let's demonstrate that. Okay, so first I create this augmented matrix with A on the left and identity on the right, and we start doing elementary row operations. Right? So first we try to get zeros in the first column. We can do that by subtracting twice the first row from the second and adding the first row to the third to get this. Now if you notice, if we take the second row and add it to the third row, we get zeros here. Right? And we're boned. Right? Nothing will ever put a 1 back in here. Right? That is, there is no elementary row operation that can turn this into the identity matrix. Right? Therefore, this cannot have an inverse. Right? And those excuse me, proposition and theorems that I was showing you before this are towards showing formally that this is the case. And that if you can't reduce this to the identity matrix, that it has no inversion. But maybe you'll save that for next year. Right? So not all matrices are invertible. Right? So thereby, A could not be elementary. Because if A was elementary, it would have an inverse by definition. Okay, so here's an application of the determinant, of the inverse, which is probably one of the most important applications of a computer. Right, so even the first computers that we conceived of were basically general-purpose machines used for solving really big linear systems. And the way that you can solve a linear system is by finding an inverse. Right, so the finding matrix inverses is big business. Right, because once you start trying to implement it with a computer, you start running into problems. And maybe we can discuss some of these problems next week. But recall from last week that if we had a linear system in n variables, that it could be written in matrix form like this. Right? So this is the linear system which takes a11 x1 plus a12 x2 and so on. So this dot product, this is a linear equation and so on. Each linear equation is equal to b1, then b2, then bm. So we can write this even more compactly as the expression ax equals b. Right? Your coefficients times some unknowns is equal to some constants. Right? However, this means if A is invertible here, this means that the solutions to the system can be recovered by multiplying on the left by A inverse. Right? So take this equation, ax equals b, and multiply on the left by A inverse, and what do we get? Well, we get A inverse ax is equal to A inverse b, which means that x is equal to A inverse b. Right? This becomes 1. And now this is an expression for the solutions. Right? A inverse b will be a vector. So I'll show you what I mean. So here's a polynomial system. Here is it expressed as matrices. Right? So this is x plus 2y plus 3z is equal to 1. And this says x plus 2y plus 3z is equal to 1. The second one says 2x plus 5y plus 3z is equal to 2. The third one says x plus 0y plus 8z is equal to 3. We already found the inverse of this. That was the first one we did. Right? So recall, the inverse of this matrix is this. Right? So I can construct the solutions to this linear system by taking the inverse and multiplying by b. Right? Those were the constants. And when I do so, you get 19 minus 6 minus 2. Right? And these are the solutions to the linear system. You can check them if you want. So what we can extract from this is, if a matrix A has an inverse, then it corresponds to a linear system which has exactly one solution. Right? And there will be no inverse if the linear system that matrix corresponds to has an infinite amount of solutions. Right? So there is a lot of interplay between matrix inversion and linear system solving. In fact, they're like functionally equivalent. So solving systems in this manner is most typical. Right? We don't really use these augmented matrices. We use determinants. Okay, so next week we're going to talk about linear transforms, which is how to take a matrix A and operate on a point to make it rotate or something like that. And I'll talk a little bit about automating Gaussian elimination with a computer. Other than that, work on your assignments. Come see me if you need any help. Enjoy your weekend, if you dare.
Does it make sense you're raising matrices to powers? Can you have powers other than integers? I mean, you presumably take the square root.
I don't know. What is the square root of a matrix? It's like I'm not sure that exists. Well, no. So you could define it if you wanted, but I'm just trying to figure out what that would mean.
And so what you're doing in finding the inverse, you're bypassing finding the determinant. Presumably, you could also just try to find the determinant, and if that's zero, you say, well,
Right, but then you may have wasted all this time proving that it's invertible, having no information about the inverse.
yeah, so it's like one might be easier to calculate than the other, presumably. So you do the
Determinant's always easier to calculate than the
so that
inverse.
would be a quick calculation. Should I go and do the inverse or try to find it? I'll just calculate the determinant first, and if that's zero, then I won't bother.
Yeah, you could do that. Yeah.
That was an interesting pattern. Like if the determinant is 0 for a 2 by 2 matrix, it's not invertible because
Because you can't
is
divide
that
by the
yeah?
term.
But is that is the same case for other?
Yeah,
like 3 by
that's
3?
true in general. But that's a little bit more difficult to prove.
So solving those linear systems that way we're just doing the covers the one solution or infinite many. How do we get no solutions from that? Like if we solve it that way, we can find that it's going to be give us either infinite or no. What kind of result would we get if when solving those that same way we were doing theirs? How would we, what would we say?
If there's no solution to the system, well, A won't be invertible for sure. So maybe, yeah, maybe if it's not invertible, then it's either no solutions or. Okay, so if it's not invertible, it's only invertible if it corresponds to a single solution, and not invertible if it doesn't, which means that that can either be infinite amount of solutions or no solutions. How to distinguish between those, I'll have to get back to you, because I don't know. Or think about it. Actually, you find out and tell me. Yeah.
And why did we just pick this definition of determinant like for 2 by 2 and 3 by 3? Like why do it that way? I'm sure we could pick another way of just timing and subtracting numbers to.
So if you see like the larger picture of how we do determinants, it's actually like makes sense for the pattern. So it's like the same way that like something to the power of 0 is 1. Like sort of doesn't make any sense. Yeah, if you look at it, yeah.
Okay.
So we get to pick our base cases sometimes, and yeah. See you soon. You want to know about the sequence? Yeah. Okay, so it's called the look and say sequence.
The only thing I could work out is that if you have like 2 pairs of numbers and you multiply them together and then added all those pairs up.
It's a lot less mathematical than that.
No? Okay.
Okay, so you have 1,
Yeah.
you have 1, 1, you have 2 1s, you have 1 2, 1 1, you have 3 1s and 1 2, you have 1 3, 2 1s and 1 2,
Oh, okay.
you have 3 1s,
So if I actually
1
read it out,
1
I would
3,
have noticed it.
2 2s, 2 3s, 2 1s, 2 2s. So the interesting thing is if you make this into a sequence, that there exists some constant, real constant, such that the limit of 2 consecutive ones is equal to C. Right, so it's amazing that something like this would have like a limiting value, because it doesn't seem to have like how would you even like write this down as like something that you could take a limit against?
Oh, is that the major 1 plus 2 plus 3
Huh?
The limit, you do the limit from 1 plus 2 plus 3 plus 4.
The limit of the sum of the first infinite numbers? Is that just going to be infinite?
You can look it up.
The sum of the first n numbers
Yeah, apparently.
is definitely infinite.
There's something, I don't know if it might be saying it wrong, but
now some of the first n numbers is n.
Well, n times n minus 1 over 2. But if you take the limit of the sum of the first n numbers, then it's infinite.
it's something like that.
You've got a series that's like 1 minus 3 plus 5 minus 7, and you just alternating with changing the sign, and then that limit is a quarter.
Oh, I think I remember it. Yeah, yeah. But that's Yeah, that one's not solved yet. Like there's one if you like choose like the closest even number divided by 2. Anyways, there's a bunch of sequences like this which sort of like defy mental reasoning. But that's the fun. This one will always screw with your friends now that you know
The
it.
only thing that I worked out, and it didn't work for all of the cases, I'm pretty sure, is
Well, the thing is, for any finite, if I give you any finite number of a pattern, no, there's an infinite number of patterns that will satisfy a finite. So you probably did find some type of pattern.
if you had that, plus that, and the other in between, and then it was the sum of the last column, like added individually.
Like at every step?
I'm pretty sure it does.
So 3 times 1 and 1 times 2 is 5. 2, 3, 4, 5. Cool. But what happens when you have this is 3 products, right? 3 plus 2 is 5. This is 7. Holy shit.
Here we go.
Nice.
Yes.
3, 6, 10. 2, 4, 7. That is extremely interesting. 5, 7, 11. Oh wait. 6, 8, 12. 6, 8, 10, 12.
I just didn't know how to work out the next row.
Well, I don't think that information is sufficient to generate more patterns.
Yeah.
But it's certainly like a really... It's a good way to check if, well, if I give you something in the sequence and it doesn't satisfy that, you can assure me that you have not found something in the sequence. But knowing that it satisfies it isn't enough to actually confirm that it should be. But that's an interesting observation. I've never noticed that.
I didn't see the simple, so I didn't talk to myself.
No one realizes this when you're shown to them. That's why it's such a great sequence.
I just had something with design.
Sure.
You said in one of the previous lectures that we could define a circle with 4 points, and it was a parabola that we could define with 3 points. And, I mean, we've got 4 unknowns.
Right, so I guess maybe I misspoke. So if you have a polynomial, like y equals x, something like that, then the degree of that, the x part, will tell you about the curve, right? So if I have 3 points, you can get a parabola, right?
So
because that's a power of 2.
Yeah, and when you've got x squared plus y squared, you
But
get
it's no longer a polynomial.
Yeah.
Well, it's no longer a polynomial in x.
Yeah.
Right.